So now we're on page 69, in which we are going to combine three vectors to come up with a resultant. And so let's walk through this. And this is Galileo all the way. This is scientific method all the way. So we start by a sketch, which Galileo calls creating a model. We'll start with a sketch. We want to find out what the combination of these three vectors of force might be. So again, using Galileo, we're going to limit the scope of inquiry, the pizza principle. We're going to evaluate each individual vector individually. So vector 1 will look like this. Vector 2 will look like this. And vector 3 looks like this. Again, we're combining pieces and parts of the scientific method, so once again we're creating models and we are limiting the scope of inquiry at the same time. Now what we'll do is we may infer that these vectors are the resultants of these forces. Like so. We'll label them accordingly. This would be opposite 1, adjacent 1, opposite 2, adjacent 2, adjacent 3, opposite 3. And recall, we're doing old school trig, so that means we're going to evaluate every angle as if it is between 0 and 90 degrees, no matter where it may lie. Now this one, we already know, is 33 degrees, and it is 3.1 newtons. This is 103 degrees, which makes it actually 77 degrees, like so. It is 2.0 newtons. This guy here is 338. Which makes it actually 22 degrees. All right, so now we're going to evaluate the component vectors using trig. We're going to set up our chart. First we'll go for the adjacents. And then we'll go for the opposites. A total, O total. And we can't lose sight of the directions. The directions are important. A1 goes like this, so A1 is positive. A2 goes in this direction, that makes it negative. A3 goes in this direction, making it positive. O1 goes up, he's positive. O2 goes up, he's positive. O3 goes down, he's negative. Now you don't have to worry about it anymore. So now we'll just bash out some numbers. So I'm going to use cosine to figure out the adjacent sides. So cosine 33 times my hypotenuse of 3.1. I got if I round it, I get 2.600. A2, cosine of 77 times my hypotenuse of 2, I got 0.450. A3, cosine of 22 times my hypotenuse of 1.6 newtons. I've got to put that there. I got 1.483. Now I'll do my O's, my opposites. That we use sine for that. So sine 33 times my hypotenuse of 3.1, 1.688. Sine of 77 times my hypotenuse of 2, 1.949. Sine of 22 times my hypotenuse of 1.6, 5.599. Now, tally them up. 2.6 plus a negative 0.450 plus 1.483. I got 3.633. Tally these. 1.688 plus, say that again, 1.688 plus 1.949 minus 0.599, 3.038. Okay, so now let's see what this guy looks like. Now remember, we always draw the horizontal vector first. So my horizontal vector A goes this way. 3.633. And my O goes like so. Which tells us that the resultant would be this guy right here with an unknown angle theta. Okay, there's our resultant, our sum total of vectors. So now we have opposite and we have adjacent. That means that we can use tangent to figure out the angle. The tangent of that angle is opposite over adjacent, which is 3.038 over 3.633. And I get a tangent of 0.836. Reciprocal function of tangent, that will give me 39.9 degrees. Now, we need to figure out the hypotenuse. Hypotenuse is going to equal the opposite over the sine of the angle, which is going to equal 3.038 over the sine of 39.9. Sine 39.9.600. Let's double check that. That's better. Sine 39.641. That's 0.641. So divide these. So 3.038 divided by 0.641, 4.739. All right, so we've solved the sum of these three vectors of force, the resultant force. Consider them like bungee cords. I could have three bungee cords pulling in these different directions. And it would be the same as if I had one bungee cord pulling in that direction. That's what we're saying here. That's what we're saying. And you know, this is Galileo all the way. Creating a model, organizing your information, limiting the scope of inquiry, logical inference and deduction. That goes all the way back to Aristotle. Organizing data again, quantitative methods, right? Creating another model, more quantitative methods. Now, let's go one step further. What would cancel the whole shebang out? Well, how about something equal and opposite? In other words, what if I had a fourth bungee cord that went in this direction? That bungee cord would cancel out this bungee cord, which in effect would cancel out these three bungee cords. That is what we call an equilibrant. We're talking about what we call a static system of forces. A static system of forces is a system of forces in which all the forces cancel each other out. And so the net is zero, right? For a reaction, there's an equal opposite reaction. You heard that, okay? Well, when you park your keister in a chair and just sit there, that is an example of a static system of forces. Your keister is pushing down with X amount of pounds of force. That chair is pushing back with an equal amount of force. You're not floating off the chair and you're not sinking down into the cushions. You're right there, okay? So static systems of forces, they're all over the place. And let's do a little evaluation here. I think we can say fairly safely that instinctively this vector would be equal but opposite that one. And you'd be right. So we're going to swing it around 180 degrees from 39.9. So 39.9 plus 180. I got 219.9 degrees. And its magnitude would be 4.739 newtons. Okay. Now, here's something else. We can also infer that this vector is made of component vectors that go like so. And so we could we could say that these vectors would be in play. Now, I neglected to mention that this is called an equilibrant. We're just going to call it vector EQ. Okay. The equilibrium vector, if you will. And so this, therefore, would be the A EQ, and this would be the O EQ. And it doesn't take a whole lot of imagination to figure out what the values of these component vectors would be. They'd be the same as their mirror images over here. So this guy right here would be 3.038 newtons. And this guy here would be 3.633 newtons. But here's where it gets interesting. My AEQ is going to be in the opposite direction, so he's going to be negative 3.633 newtons. My OEQ is going in the opposite direction as well, and he would be a negative 3.038 newtons. Now, what I want you to do at this point is grab your calculators, because I'm going to show you something here. The first thing I want you to do is I want you to add up this guy, and this guy. Go ahead and add them up, and I'll do it along with you. And I'll bet you got something really close to a positive 0.450. Something very close to that. We'll try another one down here. Let's add up this one, and this one. And I'll do it along with you. So I'm going to go 1.688 plus 1.949 minus 0.638. And I'll bet you got a positive 0.599. What's that telling you? Well, in a static system of forces, we've established that in a static system of forces, the sum of the forces is 0. But what the other thing that is important, the important takeaway is this, is that in a static system of forces, any one vector of force is equal and opposite the sum of all the others. Even these little guys here. This little guy here is equal and opposite the sum of all the other big guys. That's how a static system of forces works. Now, one other last thing here. When we look here, we see that we have made a prediction. What do you do when you make a prediction? You test it. When is it suitable to test in science? The answer is always. So that's going to be the next piece. I'm going to show you how to actually test this.